Good day, everyone. Welcome and thank you for attending Hosokawa Micron Power Systems webinar on grit reduction of carbon black. My name is Greg Boyer and I am the Marketing Manager at Hosokawa Micron Power Systems. Hosokawa Micron Power Systems is a division of Hosokawa Micron Group with headquarters in Osaka, Japan. We are the global leader in powder processing equipment, employing 1,500 employees worldwide with production facilities in 5 countries and 12 research facilities and test centers. Hosokawa Micron Power Systems is North America's division of Hosokawa Micron Group, supplying products and services in the chemical, mineral, food, and pharmaceutical markets. Our brand names include Micro, Alpine, Micron, Riconata, Majak, Stott, Vitalair, and Hosokawa BPACs. Hosokawa is the global leader of powder and particle processing solutions for size reduction, classification, mixing, and drying applications. Our division was founded in 1923 under the name Pulverizing Machinery. We are located in Summit, New Jersey, and have been part of the Hosokawa Micron Group for 23 years. I would like to introduce our presenter, Bill Brown, Division Manager of the Chemicals and Minerals Group at Hosokawa Micron Power Systems. Bill has worked in powder processing industry for 18 years, serving many roles in the Hosokawa Micron Group. Bill holds a BS degree in mechanical engineering from Rutgers University and an MBA from the University of Richmond. At this point, I'd like to turn the presentation over to Bill.
Thank you, Greg. Let me begin by outlining the topics that will be covered in this presentation. First, I will outline current market conditions, followed by discussing existing incumbent grit reduction technologies. From there, I will focus on new grit reduction technologies, specifically the principle behind grit reduction, followed by advantages. Next, I will discuss a comparison between these new technologies with respect to energy and product quality. Then I will conclude this with a summary and overall synopsis of the presentation. It is becoming more difficult for carbon black manufacturers to compete in the market with a stable of commodity products. Most recent global economic concerns, continued uncertainty in the marketplace for industrial and consumer products, fluctuating oil prices, combined with governmental and environmental regulations, are all contributing to increased production costs. Global demand for rubber products is slowly emerging from record lows. China and India are the only 2 emerging markets, while others are still suffering from drastic reductions. All of these factors are contributing to eroding revenues and product profit margins. Perhaps one way to emerge from the dilemma of low-profit commodity manufacturing may be to seek new or emerging markets with value-added niche products. In the case of carbon black, grit or residue control is one important quality parameter by which the value of a product is measured. If a manufacturer could develop a method to produce cleaner, near grit-free carbon blacks, then it could perhaps target these alternative markets by offering products that may add strength, durability, and enhanced product performance. The manufacturer could thus command higher prices, generating more revenue and higher profit margins. Before I touch on these new milling technologies, let me first begin by reviewing the incumbent technologies for which most of you, I am sure, are familiar with. Perhaps the mill that's been around the longest in the carbon black industry is the hammer and screen mill, i.e. the pulverizer. Here are some facts and features. This is a mechanical impact mill. It utilizes a static screen to control resonance time and hence the particle size distribution of the product. So inside we have a series of hammers rotating at a specified speed and upwards of about 21,000 feet per minute. Some advantages include the fact that this hammer and screen mill, can be installed in line, from the reactor bag filters to the final packaging line. It can be installed in between. In addition, this mill is relatively inexpensive. not only from a capital cost perspective, but from an operating and maintenance cost perspective. However, there are quite a number of disadvantages for a machine like this. First of all, the screen is susceptible to breakage. Any sort of tramp material or overloading of the mill could result in breaking of the screen, thus destroying the quality of your end product. In addition, even though the tip speeds are relatively high for a machine like this, it does provide or manufacture very coarse grades of carbon black with respect to some of the newer technologies out there. So when we speak about grit levels of carbon black, we're not talking about 500 mesh or 325 mesh, but more or less 35 mesh. For example, this hammer and screen mill will at best perhaps produce a product which is approximately greater than 100 ppm on 325 mesh. Another technology uses an air classifier in conjunction with an air classifying mill. These systems are most common in Asia. The idea here is to incorporate an independent separation system, removing a portion of the coarse fraction in an attempt to reduce the loading on a downstream mill or grinder. The air classifier utilizes a dynamic classifier to control particle size cut point by adjustment of a classifier speed, as well as the airflow. The air classifying mill reduces the size of the grit particles by mechanical impact. Inside the grinding chamber is a dynamic air classifier controlling resonance time and hence the particle size. Shown here is a process flow diagram of a typical air classifier and air classifying milling system. Note here that there are two independent convey systems, and the carbon black is not fed directly in line, but it is an offline process. So what we have here is upstream would be the reactor bag filters or product collectors. So the material would be pneumatically conveyed and then from there dropped by gravity into this pneumatic line, which is then feeding this air classifier. The air classifier also utilizes a secondary air inlet, hence two air inlets, the primary which is used in conjunction with the feed material, and the secondary air inlet. The coarse particles that are rejected by the classifier are dropped or discharged by gravity through a rotary airlock and hence feed the air classifying mill. The fine particles, that is, the particles without the grit, are conveyed pneumatically from the classifier to a primary bag filter, from which from that point on it's bagged or pelletized. Going back to the air classifying milling system, in comparing this technology with perhaps a hammer and screen mill, or for that matter an air classifier mill that is not utilizing an air classifier upstream, the idea here is to minimize the overall size of the air classifying mill, hence the kilowatts or installed horsepower in the system. However, despite the fact that there could be a reduction in the energy required for the milling portion of it, please keep in mind that the fact that we have two independent convey systems adds significantly the amount of capital equipment as well as the capital cost and energy cost of the overall system. So in discussing the advantages and disadvantages of an air classifier plus an air classifying mill, as I mentioned before, some advantages include reduced loading on the ACM, hence a reduction in the grinding energy, or a smaller air classifying mill. This unit is offline, therefore it could be a flexible system. Hence, lower process temperatures can be realized or utilized. As I mentioned, some disadvantages include a much higher capital cost, a higher energy and operating cost per ton of product. In certain cases, it could be 2 to 3 times that of other technologies. And also higher grit levels, coarser end products as compared to these new technologies I will be discussing. There is indeed a way to manufacture cleaner, near grit-free carbon blacks with comparatively low capital or little capital investment. There are two types of grinding mills that have recently been developed for superior grit reduction. They include the vertical long gap mill and enhanced air classifier mill. These mills have been optimized over the recent years to provide unparalleled grit and residue control, as well as excellent dispersion properties for most grades of carbon black. Shown here is the vertical long gap mill. The mechanism behind the vertical long gap mill include tip speeds, or rotor tip speeds, or hammer tip speeds of about 115 meters per second, or about 23,000 feet per minute. These tip speeds are very close in velocity to the hammer and screen mill. However, what separates this type of mill to other milling technologies for carbon black is the stressing mechanisms that are executed or employed. The Incumbent Technologies, which would be the hammer and screen mill, or for that matter an air classifying mill, utilizes mostly impact, mechanical impact. However, the vertical long gap mill is 80% or utilizes 80% particle upon particle collisions or attrition to reduce the particles, and 20% mechanical impact. So there's a noticeable difference in the stressing mechanisms for the vertical long gap mill as compared to the mechanical impact mill. This mill utilizes a stacked rotor assembly as well as an internal high efficiency classifier, and hence there's a vertical long gap, which I'll show in one of the following slides. What we're showing here in these two photos, the photo on the left, we're showing this high efficiency classifier mounted on the top or above the rotor stack assembly. Here you can see multiple stacks of rotors. You can see the different levels of hammer plates. Shown on the chart over here to the right, or the photo on the right, we have the door open here, and you can see the multiple deflector liner that's around the hammer or rotor section. However, in between the hammer plates and the liner, there's a very tight clearance in the range of, say, 3, 4, 5 millimeters, in that range. So, hence the term vertical long gap. Some other facts and features of this type of technology is the fact that this mill can be installed in lines utilizing processed gas streams in upwards of 200 degrees Celsius. In addition, this vertical long gap mill can be installed offline or even inline after the reactor bag filters. Here's a process flow diagram of a typical vertical long gap mill. Not only is the feed carbon black, but also the air are conveyed in the mixture together. They're pneumatically conveyed through this inlet duct. The feed material and the air enter the grinding chamber from below the lowest rotor stack. Shown here, you can see a couple of hammers, and here are the multiple stacks of rotors here. So the feed material and the rotor stacks enter in from below the lowest rotor or lowest hammer plate. From there, the particles work their way up slowly from stack to stack. Now, what happens behind each of these hammer plates, as the hammer plates rotate past this serrated liner, you have a series of vortices behind these hammer plates, and then these vortices are where the particles collide off each other. That gives excellent grinding efficiency as compared to other milling technologies. Ultimately, the particles are conveyed up. They get caught behind these vortices, but do work their way up this fine gap, or this vertical long gap, until the particles are presented to this high efficiency air classifier. The particles that are fine enough are removed through the air classifier and get conveyed downstream through a material handling fan to a product collector. The materials that are too coarse, hence the grit particles, are rejected by this classifier. What we have outside here is we have what we call our external recycle loop, which is comprised of a venturi operating at a specified pressure, and there's a gate here. So what happens is the particles are rejected by the classifier and are thrown out due to the centrifugal force of the particle as well as the induced flow created by the venturi. So the coarse particles are brought out, removed externally, and are carried back in and reintroduced with the virgin feed material here. So in comparing this to, for example, an air classifying mill which utilizes an internal recycle, the vertical long gap mill utilizes an external recycle loop, such that once the particles are ground fine enough, they are accepted finally through the classifier and get collected into the final product bag filter. Another technology I would like to discuss for superior grit removal includes the enhanced air classifying mill. Similar mechanisms are employed here with the enhanced air classifier mill in comparison to the vertical long gap mill. First, tip speeds are similar in the range of 115 meters per second, or 23,000 feet per minute. However, the stressing mechanisms are different than the vertical long gap mill, as I mentioned previously, whereas about 80% of the stressing mechanism is due to mechanical impact and 20% from particle upon particle collision. Please note here that there have been some modifications to a standard air classifying mill here, specifically for carbon black. As with the vertical long gap mill, this type of technology can handle process streams in upwards of 200 degrees C and can be installed offline or inline after the reactor bag filters. Here's a flow diagram of an enhanced air classifying mill. Similar to that of the vertical long gap mill, the feed material, or the feed carbon black, mixed with the air is conveyed pneumatically, shown here, into the bottom of the grinding chamber. The feed material and the air are introduced from below the rotor disc. Shown here is a rotor disc with a series of hammer plates. Just one stack or one row of hammer plates in comparison to multiple stacks for the vertical long gap mill. The particles are introduced below the rotor, giving all the particles a chance to pass through the grinding zone. Given the fact that the carbon black has a very low bulk density, we want to ensure that we are passing through the grinding zone prior to the introduction to the classification zone. So the particles are passed through the grinding zone and are introduced to the classifier. Shown here is a dynamic air classifier, a high efficiency classifier. The particles that are fine enough are removed through the classifier, and then from then on are conveyed through a material handling fan and then finally a product filter. The particles that are too coarse are drawn out centrifugally, are helped out with the addition of a venturi similar to the vertical long gap mill at a specified pressure and a gate. All these principles here, or all these parameters, affect the recirculation. So the coarse particles are rejected and are recirculated externally, similar to that of a vertical long gap mill, yet different from a typical air classifying mill. As I will highlight later in this presentation, not all grades of carbon black process similarly. Rates and product quality vary from grade to grade. In order to define product and process performance, pilot testing is a must. End product quality and production capacity can be determined from trials. Process data such as airflows, pressures, and power consumption dictate sizing of ancillary equipment, such as material handling fans, bag filters, rotary airlocks, as well as utilities. What I'm showing here is a typical pilot plant setup or process for either a vertical long gap mill or an enhanced air classifying mill. On a pilot scale setup, since this cannot be simulated in line at a customer's facility, this is an offline process. So in this case, we're metering the feed material in with utilizing a volumetric screw feeder, then conveying it into the grit reduction mill, albeit a vertical long gap mill or an air classifying mill enhanced version. The grinding is taking place here and then pneumatically conveyed to a product collector. And here the product passes through a discharge valve or set of valves. Unlike a typical inline process, instead of having a material handling fan located between the grinder and the product collector, we have a fan downstream of the product collector pulling vacuum. Shown here is a chart comparing results of a vertical long gap mill to an enhanced air classifying mill for varying grades of carbon black. What I'm showing here actually are 4 different grades of carbon black. And the quality measure in this case would be grit levels on a ppm scale plus 325 mesh and plus 500 mesh, utilizing a water wash residue test. What I'd like to point out here is how much better on average, or how superior the quality of the product is for a vertical long gap mill, even in comparison to the enhanced air classifying mill. For example, for grade 1 with a feed of 250 ppm plus 325 mesh and 400 ppm plus 500 mesh, the vertical long gap mill can make a product with either 0 or 1 ppm plus 325, or 0, 1, or even perhaps as much as 2 ppm on 500 mesh. With that same feed material, the enhanced air classifying mill can make a similar product with respect to the plus 325 mesh, being 0s or 1s. However, please refer to this data here. Utilizing an enhanced air classifying mill, we can achieve qualities in the range of less than 10 ppm on 500 mesh in comparison to less than or equal to 2 ppm. Going down the list here, you can see how the results compare. But the trending is obvious. The vertical long gap mill, especially when in comparing or looking at the plus 500 mesh, provides a much superior product quality to even that of the enhanced air classifying mill. There are two ways the process can be implemented, either offline or inline. For offline systems, the mill is separated from the pneumatic line, from the reactor bag filters to the primary bag filter. Aside from the fact that the system can be operated at ambient temperatures and not at elevated temperatures as found at the outlet of the reactor bag filters, the feed rate to airflow ratio can be controlled. Shown here is an inline process integration, utilizing or employing either a vertical long gap mill or enhanced air classifying mill. So what we have in the existing carbon black process would be the reactor bag filters, or a series of reactor bag filters. Typically there will be multiple filters discharging through these valves to a common convey point. From there, the product is either utilizing or employing a hammer and screen mill or nothing, and being conveyed from that point from the reactor bag filters to the primary bag filter where the material is then packaged. However, as I mentioned previously, either mill can be installed in line. So what we have modified or retrofitted would be cutting the pipe essentially from the discharge of the reactor bag filters to the inlet of the primary bag filter and installing a new pneumatic line or new convey line, followed by one of the grit reduction mills. And downstream of the grit reduction mill, due to the fact that there is now increased pressure drop caused by the loss across the mill, we do need to compensate that additional pressure loss by installing a material handling fan to compensate, to drive it via positive pressure from this point, the material handling fan, to the product collector. Here's some facts with regard to the inline process integration. Mills can be sized to meet the capacity of the grade or grades of carbon black. Nominal convey rates of 40 to 1 or 50 to 1 pounds of carbon black per standard cubic foot of air volume are typically utilized. In addition, material handling fans or blowers are required to handle additional pressure drop across these mills. Pressure drop varies with process conditions, and these pressure drops can be determined from pilot testing. Pressure drop across a vertical long gap mill is, on average, higher than that of an enhanced air classifying mill. And in such, a higher energy requirement for a vertical long gap mill is employed or realized, however, with much better performance, that is, a better product quality. And I'd like to show you this example. In this case, I'm utilizing or comparing a 150 horsepower enhanced air classifying mill to that of a 300 horsepower vertical long gap mill. Please refer to the chart here in comparing the 150 horsepower grinding enhanced air classifying mill to that of that 300 horsepower vertical long gap mill. The capacities are pretty close here, 4.5 tons per hour as compared to 5 tons an hour. Note here the airflow for the 150 horsepower mill is slightly higher than that of the vertical long gap mill. However, the pressure drop across this mill, the vertical long gap mill, is much higher than that of the enhanced air classifying mill. So in taking into account the additional pressure or static pressure requirement, the actual blower size is much higher for that of a vertical long gap mill. In this case, 165 kilowatt motor for the blower as compared to 110 kilowatt motor. And in comparing the overall energy required or the installed horsepower or kilowatts for an enhanced air classifying mill as compared to the vertical long gap mill, in looking at the unit energy at the 4.5 and 5 tons an hour, please note here that the energy requirement is about 50% higher for a vertical long gap mill than that of an enhanced air classifying mill. That is 53 kilowatt hours per ton versus 78 kilowatt hours per ton. In conclusion, the vertical long gap mill makes the cleanest, best quality product. However, despite the fact that the enhanced air classifying mill produces a slightly subpar product in comparison to the vertical long gap mill, it does significantly outperform other existing technologies, hence making lower grit levels than existing or incumbent milling technologies. Both mills can be retrofitted inline in existing processes. These machines are versatile and flexible. Either mill can be adjusted to handle varying grades of carbon black. Production of a value-added product to satisfy the demands in a niche market at a higher sale price and thus a higher profit margin. Thank you very much for your time and attention.
Thank you, Bill. We'd like to thank you for your time and attention today. Please refer to our website, www.hmicronpowder.com, to view upcoming educational webinars and previously recorded programs. If you have any further questions or requests, you may contact Bill Brown. His contact information is being displayed here. Please feel free to share this program with your friends and colleagues. Thank you very much and have a good day.